Exercise 1.1. Determine whether each of the following relations are reflexive, symmetric, transitive. Here given set is A is equal to 1, 2, 3 up to 14 and relation R equal to ordered per x comma y, and the condition is 3x minus y equal to 0. So first, for reflexive, the condition, the condition, that is if ordered per a comma a belongs to R for every a belongs to capital A. For every a in A, that is ordered part should be present in capital R. Here the relation R is the given condition ordered per x comma y such that 3x minus y equal to 0. So 3x minus y equal to 0 means then y equal to 3x. So we have to take x equal to 1, y value is 3, x equal to 2, y is equal to 6, x equal to 3, y equal to 9, x equal to 4, y equal to 12, x equal to 5, y equal to 15. So 15 is not present in the set. So this will not, we will not take the x equal to 5 and y is equal to 15. For the relation then R equal to ordered per 1 comma 3, 2 comma 6, 3 comma 9, 4 comma 12. For every a in A, that is ordered per a comma a belongs to capital A. For every, that is for every element in A, that is 1 comma 1 is not present in the relation, 2 comma 2 is not present in the relation, 3 comma 3 is not present in the relation, 1 comma 1, 2 comma 2 up to that is 14 comma 14 not present, does not belongs to relation. So our relation R is not reflexive. Then for symmetry, we know the condition is if ordered per a comma b belongs to R, then b comma a should present in R. For all a comma b belongs to capital A. If we take that is 1 comma 3 belongs to R, then 3 comma 1 is not present in R. So therefore our relation is not symmetric. Third condition, transitive. If we take two ordered pairs, AB belongs to R and BC belongs to R, this implies A comma C should present in R for all ABC should present in A, belongs to A. So if we take 1 comma 3 belongs to R and 3 comma 1, 3 comma 9 in R, then 1 comma 9 is not present in 1 comma 3, 3 comma 9, that is A comma C. Here A value is 1 and C value is 9. So 1 comma 9 is not in R. So our relation R is not transitive. Therefore our relation R is not an equivalence relation. Second subdivision, n equal to 1, 2, 3, set of all natural numbers, and R equal to x comma y such that y equal to x plus y, condition is given, and x less than 4. So x less than 4. So we have to take, that is x less than 4, we have to take that numbers 1, 2, 3 and y equal to x plus 5. So when x equal to 1, y is equal to 1 plus 5, that is 6. When x equal to 2, 2 plus that is 5, 7, x equal to 3, that is y equal to 8. So our relation R equal to ordered pair, that is 1 comma 6, 2 comma 7, 3 comma 8. First we have to check reflexive. We know the condition is if ordered pair, that is A comma A, belongs to capital R for every A belongs to capital A. That is for every element in A, that is 1 comma 1 is not present, 2 comma 2 is not present, 3 comma 3 is not present in our relation. So R is not reflexive. So 1 comma 1, 2 comma 2 is not present in R. So our relation R is not reflexive. Second one, symmetric. Symmetric condition is if ordered pair A comma B belongs to capital R, this implies B comma A belongs to capital R for all AB belongs to capital A. That is, if we take, that is 1 comma 6 in R, 6 comma 1 is not present in R. So our relation R is not symmetric. Transitive. If AB belongs to R and BC belongs to capital R, this implies A comma C belongs to capital R for all ABC belongs to capital A. If we take, that is our relation R equal to, that is 1 comma 6, 2 comma 7, 3 comma 8. 1 comma 6 is present in R, 2 comma 7 present in R, but 6 comma some numbers is not present in R. So that is 1 comma 6, 2 comma 7 in R and 3 comma 8. So 1 comma 6 means here R, but B comma C, 6 comma some value is not present. If we take, that is 2 comma 7, 7 comma some number is not present in R, 3 comma 8, that is 8 comma C, that is a C value, C may be some number that is not present in R. So our relation R is not transitive. Third subdivision, that is A is equal to 1, 2, 3, 4, 5, 6. The given set is A and relation R equal to ordered pair X comma Y such that Y is divisible by X. So R equal to Y should be divisible by X. Then 1 is divisible by here X comma Y. So Y should be divisible by X. So 1 is divisible by 1. So our next number, that is 2. 2 is divisible by 1. If we take 3, Y is 3. 3 is divisible by 1. 4 is divisible by 1. 5 is divisible by 1. 6 is divisible by 1. Next we take 2. 2 is divisible by 2 but not divisible by 3, but not divisible by 4, not divisible by 5, not divisible by 6. When divisible by 4 we get some value, that is a remainder. So next 3. 3 is not divisible by 2. 3 is divisible by 3. 3 is not divisible by 4, not divisible by 5. 3 is divisible by 6 means some value we get in fraction. So 3 comma 3. So next 4. 4 is divisible by 2. The remainder is 2. Then 4 is not divisible by 3. 4 is divisible by 4. Does not divisible by 5. 4 by 6 means that is some 0.0 point something. So next 5 is not divisible by 2. 3, 4, 5 is divisible by 5 and not divisible by 6. Then 6 is divisible by 2. 6 is divisible by 3. 6 is not divisible by, that is 6 is not divisible, that is 6 divides by 4 means some, that is 2 by 3 in fraction. So 6 is not divisible by 5. So 6 is divisible by 6. This is our relation. Then we have to check the reflexive. That is, condition is if ordered per A, comma A belongs to capital R for every A belongs to capital A. For every AA, that is 1, comma 1 is present in our relation R. 2, comma 2 is present, 3, comma 3 is present, 4, comma 4 is present, 5, comma 5 is present, 6, comma 6 is present in our relation. Therefore, R is reflexive. That is 1, comma 1, 2, comma 2, 3, comma 3, 4, comma 4, 5, comma 5, 6, comma 6 present in R. So, our relation R is reflexive. Next, symmetric. Symmetric condition is if ordered per A, comma B belongs to capital R, that is A, comma B means that is B, comma A should present in R. For that is all A, comma B belongs to capital A. If we take that is 1, comma 2 is present in R, 1, comma 2 is present means present in R, 2, comma 1 is present, 2, comma 1 is not in R, but 2, comma 1 not present in R. Therefore, R is not symmetric. Next, transitive. If ordered pair, that is AB belongs to capital R and B, comma C present in R means this implies A, comma C should present in R for all A, B, C belongs to capital R. If we take that is 1, comma 2 in R and 2, comma some value 2, comma 4, we take 2, comma 4 belongs to capital R. Then 1, comma 2, A, comma C. Our condition is A, B belongs to R, B, comma C belongs to R means then A and C should present in R. Here A value is 1 and C value is 4. 1, comma 4 is present in R. We have to check 1, comma 4 belongs to R. So R is transitive. Fourth subdivision, that is Z equal to set of integers 0 plus or minus 1 plus or minus 2 plus or minus 3 etc. R equal to ordered per x comma y such that x minus y is an integer. So our relation when subtracting, that is x minus y, if we take 0, comma 1, 0 in x and y in 1, 0 minus 1 that is should be is an integer. Then 0, comma 2, 0 minus 2 that is minus 2 is an integer. Likewise 1, comma 2 means that is 1 minus 2 that is minus 1 minus 1. Any integers if we subtract we get a integer. So R equal to 0, comma 1, 0, comma 2 we get the whole set, that is Z cross Z. So first we have to check reflexive. So reflexive, that is condition is if A, comma A belongs to capital R for every A belongs to capital A. That is here 1, comma 1, that is 1 minus 1 we get the ordered one is an integer 0. Then 2, comma 2 that is 0. 3, comma 3 0 is present in R. So that is belongs to R. So our relation R is reflexive. Next is symmetric. The condition is if ordered per A, comma B belongs to R, this implies B, comma A belongs to capital R for all that is A, B should present in our set A. So if we take that is 0, comma 2 belongs to R means that is 2, comma 0, that is 2 minus 0 is an integer that is also present in R. So 2, comma 0 is also present in R. So therefore our relation R is symmetric. Transitive. The condition is AB belongs to capital R and BC belongs to capital R. This implies A, C should present in R for all A, B, C belongs to capital R. That is, if we take that is 1, 2 in R and 2, 3 in R, this implies that is 1, 2. 1 minus 2 is minus 1 is an integer. 2, 3 that is 2 minus 3 is an integer is present in our relation. So 1, that is 1, 3. 1, 3 is also present in